So very good morning one and all. In this class we will discuss about kinetics of enzyme catalysis. So in the previous class we have discussed about the kinetics of photochemical processes or photophysical processes, where we have also applied the steady state approximation, which is suitable for the substrate concentration if it is used in low concentrations of substrate. Similarly, let us try to understand the kinetics, how kinetics can be applied, kinetics can be understood for the enzyme catalysis. So we will start our discussion with understanding the enzymes, their structures, and throughout this class, like these are the important points that we will be discussing. One is like enzymes. About enzymes we will be studying. Enzymes are homogeneous and biological catalysts. And then this enzyme kinetics is understood through Michelson-Menten mechanism. And then from the Michelson-Menten mechanism, by applying that, we will be deriving an equation known as Lineweaver-Burk plot, which will be helpful for us to calculate various parameters like kinetic turnover frequency, catalyst efficiency of the enzyme, etc. Similarly, like we will be assessing the efficiency of the enzymes through turnover frequency and the number of cycles it can efficiently perform for the given set of reactions, etc. So let's begin our lecture with the understanding of enzyme. Enzymes are homogeneous biological catalysts. So these ubiquitous compounds are either special proteins or nucleic acids that contain an active site. That active site is responsible for binding the substrate or the reactants and then slowly converted into products. The most important part of this enzyme is the active site. So this active site is specific for the specific substrates that it catalyzes. So all enzymes does not work for all the reactions. So you require certain specific enzyme and substrate interactions that are helpful for the reaction to carry out. These substrate and enzyme reactions interactions are like different, like hydrogen bonding interactions, electrostatic interaction, or van der Waals interaction, through which substrate binds to the enzyme, and then the reaction proceeds for the formation of products. There are two models that can help us to understand the enzyme and substrate interactions. One is the lock and key model. So this lock and key model, in this lock and key model, substrate has a specific configuration which fits well with the active site of enzyme, and then the reaction carried out, it is converted into products. And second one is induced fit model. Experimentally, induced fit model is the best suitable model for understanding the enzyme catalyst, and which is also applicable for wide variety of reactions and wide variety of enzyme catalysis. In this induced fit model, the substrate, based on the substrate, enzyme undergoes conformational changes and adopt a configuration that is suitable for the substrate to come and fit into that, which is like induced fit. So enzyme conformational changes induce fitting of substrate into the enzyme that converts in, then the reaction goes on, converted into products. After the product formation, the product leaves this active site, so enzyme is regenerated. In this way, the enzyme undergoes several cycles of reaction. So one enzyme can accommodate several times the substrate and convert it into product, and it is regenerated, which is a typical way of catalyst action. So to understand this enzyme kinetics, so Michelson-Menten mechanism is widely followed and widely applicable. So we have a few notations that required to understand this Michelson-Menten mechanism. One is S. S stands for the substrate. S naught stands for the initial substrate concentration. E naught stands for the initial enzyme concentration. and then when these two are combined, they undergo the formation of enzyme substrate complex. So after any point of time in the reaction, the concentration of substrate is written as S without any subscript. So after any point of time in the enzyme concentration is written as E without subscript 0. That indicates like the concentration of substrate and enzyme after certain point of reaction. And after that, another important point is the concentration of enzyme and substrate. In certain cases, like you will have substrate concentration very much higher than the enzyme concentration. So in that case, the rate of reaction depends only on the enzyme, much similar to what you see for pseudo first order reaction, where one of the substrate, if you are taking in very high concentration, the rate of reaction does not depend on it. The reason is like when you are taking very high concentration of any one substance, very little amount of that one is reacted, so more or less the concentration is maintained, so it is almost like independent, rate of reaction is independent of that concentration. Similarly, if you take substrate concentration very high in any case in the presence of an enzyme, so enzyme is the most enzyme concentration is the most probable parameter for us to understand this kinetics. So the rate of this rate of reaction, we call it as maximum velocity. Okay, let us try to understand like how this Michel's-Menten mechanism helps us to understand this enzyme catalysis. As usual, like this undergoes like in two steps. In first step, enzyme reacts with the substrate, forms a enzyme substrate complex through the conformational change of enzyme. Enzyme accommodates the substrate and it forms a ES complex, enzyme substrate complex. The rate of formation of this enzyme substrate complex is K1. Now this formed enzyme substrate complex has two chances. Either it can go back to its native place, in native position, like enzyme is regenerated and substrate is regenerated, so no net reaction. Whereas this enzyme substrate complex can also form the products with enzyme regeneration with a rate constant of K3 as given here. So in these two, step 1 is fast step and step 2 is slow step. As we know, like as we understand, when you have a multiple elementary steps in a reaction, the rate of a reaction depends upon the slowest step. So here step 2 is the slowest step. The rate of product formation depends upon step 2. So based on that, we can write the rate of reaction as dP by dt. The rate of product formation is equal to rate constant K3 multiplied by concentration of ES, that is substrate concentration. In usual, like substrates, enzymes are taken at least 1/3 of the concentration of substrate. Even then, these enzymes are very much active as a catalyst. So when you are using at low concentration, you can apply steady state approximation to the intermediate formed. That the steady state approximation says the rate of formation of intermediate and rate of decomposition of intermediate are same. That means as soon as the substrate intermediate is formed, it is converted into product. When we apply steady state approximation, we can write it as K1. The one is like on left hand side we write the formation and right hand side we write the decomposition. So formation is the step 1 forward reaction, so that K1 into concentration of E and S, which is equal to two decomposition steps. Decomposition step 1 is the backward reaction of step 1, that is K2 into concentration of ES plus K3 into concentration of ES. From this one we can write the intermediate concentration ES as K1 into concentration of E into concentration of S by K2 plus K3. Okay, this is what we have got. Concentration of ES now we have written. Now the one important parameter here is like we would like to have a term that we have in control. For example, like enzyme concentration E stands for enzyme concentration after specific amount of reaction. So to monitor that one, it is always better if you have initial concentration, because initial concentration is controlled by us, that we are giving the desired amount of initial concentration. So for this one we can write the concentration, total concentration of enzyme as enzyme reacted plus enzyme unreacted. Enzyme reacted is ES, substrate complex, enzyme unreacted is E. Okay, it is similar as, like, suppose if you are taking 100 molecules of enzyme in the reaction, and 80 are reacting and 20 are non-reacting. So at any point of time in the reaction, total amount of enzyme is equal to enzymes reacted plus enzymes unreacted. Exactly what it is written, the expression E naught is equal to concentration of enzymes unreacted plus concentration of enzymes reacted. From this we can write the concentration of enzyme as E naught minus ES. Substitute this expression into second equation, we will get concentration of enzyme substrate complex as K1 into concentration of S, E naught minus ES by K2 plus K3. Now let us further simplify this expression for wide application. So divide this by ES. This is all we are doing, different mathematical steps for making a simplest possible equation. If we divide by ES, you will get here K2, and this one is K3, which is equal to K1 concentration of S E naught by concentration of ES minus K1S. From this one we can write again the concentration of ES as K1 E naught into S by K1 plus K2, K1 into concentration of S plus K2 plus K3. Here we have converted the enzyme concentration into initial enzyme concentration. So this is what the expression that we have got. From this, here we would like to further simplify this one by dividing by K1. So that gives you rate of reaction as K3 into concentration of E naught S by Km plus concentration of S, where this Km is known as Michelson constant, which is given by K2 plus K3 by K1. If you remember, K2 and K3 are the decomposition of the intermediate form, that is enzyme substrate complex formed, and K1 is the formation of enzyme substrate complex. And now the same expression, rate is K3 into concentration of E naught into S by Km plus concentration of S. For maximum velocity, as we have told, like for the maximum rate of reaction, all enzyme has to react and form the enzyme substrate complex. That means enzyme is working with its 100% efficiency, where you will get the maximum amount of yield, which is expressed as maximum velocity in enzyme catalysis. So rate maximum you will get when you have E naught concentration same as ES. So you just substitute for rate. For rate, this one is E naught. For rate maximum, this is the expression that gives you the rate maximum. So you substitute E naught in place of ES in place of E naught. You'll get K3 into concentration of ES into S by Km plus concentration of S. Okay. This can be written as our rate maximum is equal to K3 into concentration of E naught, which is equal to Vmax, that is maximum velocity. So now the Michelson-Menten equation can be written as R is equal to K3 into, in the place of K3 into E naught, we write Vmax into concentration of S by Km plus concentration of S. So this is what the expression we have got. Let us try to apply these to different conditions. The condition number one is when you have low concentration of substrate, low substrate concentration condition. So where you will have, since the concentration of S is very low, Km value is always much higher than S. In that case, Km plus S can be written as Km. That will give you the final expression as rate is Vmax into concentration of S by Km. So here Vmax and Km are the constant values and S is the variable. So here rate is directly proportional to concentration of S. That means at low concentration of substrate, the reaction goes with first order kinetics, whereas when you have higher concentration of S, S value will be higher than Km. So you will get here as rate is equal to Vmax into concentration of S by S. That will become rate is same as Vmax. So that is pictorially represented here. On the x-axis you have concentration of substrate, on the y-axis you have rate. So in the initial concentration, in the low concentration stage, rate is directly proportional to S, that is first order kinetics, and at higher and higher concentration when it go, rate does not depend upon any initial concentration of substrate, so it will become zero order, and where also you will get the maximum rate that enzyme can give at that concentration. Okay, the same equation now can be rewritten in such a way that you can get a linear form of the equation, which is much easier to understand and apply. So for that one, what it is written is like here, reciprocal of R is taken, rate is taken, which will give you Km plus S by Vmax into S. Here this is a mistake, this is Vmax into S. Okay, this is not plus, Vmax multiplied by S. So that will give you 1 by R. Now you can split this one as 1 by R is equal to Km divided by Vmax into S plus concentration of S by Vmax into S. If you look at both expressions, you can here you can cancel out substrate concentration in the numerator and denominator. You will need to have the equation 1 by R is equal to 1 by Vmax plus Km by Vmax into 1 by S. If you remember, if you carefully notice this one, this will be same as y is equal to mx plus c. This is mx plus c, where x is 1 by concentration of S and y is 1 by rate. So if you take 1 by rate as y-axis and 1 by concentration of S as in x-axis, you will get slope as Km by Vmax is the slope of this one, and intercept as 1 by Vmax. This kind of expression is known as Lineweaver Burk plot, which is extremely helpful to understand the enzyme kinetics. Now the efficiency of this enzyme can be understood by calculating the turnover frequency. This turnover frequency by definition is the number of molecules of substrate converted into product, okay, divided by the amount of enzyme, number of molecules of enzyme that you have used and this conversion, the time interval in which this conversion has taken place. Okay, so this will give you the turnover frequency, which is helpful for us in calculating the efficiency of any enzyme. So this turnover frequency in enzyme catalysis is also same as K catalysis, that catalytic constant, which is equal to Vmax by E naught. Vmax is the rate maximum, E naught is the initial enzyme concentration. So that means like TYF you will get higher when you have low concentration of enzyme, and if this low concentration of enzyme can induce the high rate of reaction, that gives you turnover frequency. It is easy to understand, because with the smaller amount of enzyme you are inducing maximum rate of reaction. If you have that kind of an enzyme, that enzyme will have higher turnover frequency. The catalytic efficiency can be calculated with the help of this turnover frequency. Catalytic efficiency is turnover frequency by Km. So catalytic turnover frequency is K3 by E naught. So K3 by Km will give you, so turnover frequency is K3. So K3 by Km will give you the catalytic efficiency, where K3 is Vmax by E naught into 1 by Km. Okay. So this expression will help us to calculate the catalytic efficiency of any enzyme. So let us try to solve a few problems. Based on that, we will have a better understanding of enzyme catalysis. Here is an example that it is given for an enzyme catalyzer reaction. The Lineweaver Burk plot has the following data. Slope is given as 405 and intercept is 4 millimoles per liter per second inverse, and if the initial concentration of enzyme is it is in nanomolar concentration. What is catalytic efficiency? Now one important factor you need to remember is like always when you are doing the enzyme catalysis, take the concentration in molar quantity only. Okay, if you are given with any other units, you have to convert that unit into molar concentration and then do the calculation, because all these enzyme catalysis are explained based on the concentration of substrate in molarity, in moles. Okay, here you are given with two all the information is provided to you. One is the slope. What is slope? Slope is Km by Vmax, and intercept is 1 by Vmax, which is 4 millimole per liter. So what you need to calculate is catalytic efficiency. For calculating catalytic efficiency, you need Km and E naught. So Km can be calculated from the slope. Here slope, first we will use the intercept 1 by Vmax. So 1 by Vmax is, intercept is 1 by Vmax, which is given as 4 millimole per liter per second. So millimoles I am converting into moles. When you are convert millimoles into moles, that will become molar. 1 by Vmax is molar. So 4 into 10 power minus 3 molar. Okay, and now if you substitute that into slope equation, slope is 405, which is equal to Km divided by Vmax, or Km into 1 by Vmax, that is Km into 4 into 10 power minus 3. So from this Km will become, Km is equal to 405 divided by 4 into 10 power minus 3. This will give you approximately, this is 10 square 100, and if it goes up, Km will be, the value of Km you will get it as 10 power 5. So if you further do this calculation, you will get the K3 value as 10 power 11, and the efficiency is K3 is equal to, catalytic efficiency is K3 by Km, which you will get it as 10 power 7. So with that, these are the like different kind of equations that will help you to understand the enzyme catalysis. And now let us try to go for another problem. For an enzyme catalyzer reaction, the plot of inverse of initial rate against inverse of initial substrate concentration, that is 1 by R versus 1 by S, which is nothing but Lineweaver Burk plot, for which intercept is 1 by Vmax and slope is Km by Vmax. Okay, intercept 1 by Vmax is given as 2.12 and Km by Vmax is given as 0.16 seconds. So this is already given in moles per liter. So moles per liter is molar, so you don't need to do any conversion. You can straight away substitute this 1 by Vmax value into this one. So this one I am writing it as Km multiplied by 1 by Vmax, which is equal to 0.16 seconds. So from this, Km multiplied by 2.12, which is equal to 0.16. So Km value from this can be calculated as 0.16 divided by 2.12. So that calculation of this one will give you the Michelson-Menten constant value. So in that way we can able to understand the enzyme catalysis, and we can able to calculate from the Michelson-Menten mechanism the different parameters that helps us to evaluate the efficiency of any particular enzyme for the given type of reaction. Okay, so I hope like this this video is helpful for improving your understanding or understanding in detail about enzyme catalysis and the kinetics of enzyme catalysis. So in the upcoming class we will discuss further more on the kinetics of different kind of reactions. So like in the next class we will be discussing about the concentration of salt concentration on the kinetics of ionic reactions. Thank you for listening. Thank you for your attention.